Okay, is the mic loud enough for you to hear me? Is it actually on? Yay or nay? Sort of. Okay. So we're going to pick up from where we left off last week. Sorry for not being able to make office hours. I was sick and just couldn't make it. Didn't feel good enough to be here. So we're going to review pointers today, hopefully finish up with C, and then move into the actual course content. Some of you guys were confused about the current assignment being in C++. You could C is a subset of C++, so if you want to write pure C code for the assignment, you absolutely can. Though if you want to use C++, that's fine, and you'll probably find that there are some things in C++ that make some tasks a little bit easier. For example, there's a string class in C++ that makes building strings a lot easier than if you try to work with a C string, which is again an array of characters that ends with an old character. I've also seen a few of you guys stop by office hours for help on the homework. It's great that you guys have questions, and I'm happy to see that you're working on them. But like I said in my announcement when the assignments were up, we haven't covered enough for you to be able to do them. So if you look at the assignments, you're like, I have no idea what to do. That's normal because we haven't covered those topics yet. If you do want to review those assignments and look through them to see what we're going to be doing, perfect. If you want to be able to do them, read chapter 1 in the book and read through the slides about information representation, and you'll know enough to be able to complete them. But if you haven't done those two things yet, I would say probably don't ask me questions about how to do the homework because I have to give you like an entire lecture to be able to do an assignment. Sound good? Yeah, Mira?
Timing-wise, aren't these programs due next Monday?
I have to change the due dates because I wasn't expecting to have to do this here. So they'll be pushed back to be a reasonable date for when I do.
So we shouldn't start until you lecture on.
I mean, yeah, if you want to start ahead, that's fine. But like, if you're coming to office hours for help, and like I have no idea like why the representation of like 3.75 is 1.111 times like 2 to the whatever, I can't like really like cover that in a succinct amount of time. And the content that you need is in the book. But we're gonna pick up from pointers. So what does the ampersand serial symbol mean? So when you see ampersand variable, what are we doing here? Right? This is the address of var. What's the type of the expression? So assuming, if var was of type t, what's the type of ampersand var? So if var's type is t, ampersand var, its type is... So if we had this, right, t var, we do ampersand var over here. What's the type of the expression? T star. It's a pointer to t, right? What do pointers hold? Addresses, right? And so if the ampersand operator is the address of a variable, right, you should expect to get an address, right? And addresses are held in pointers. So we would expect whatever var's type is, we should expect to get a pointer to that type. Does that make sense? How many ampersands can you put in front of a variable? 1, right? Because you can't ask for the address of an address. It's nonsense. When you do type star, right, what does this mean? Right? If we have some type t, right, we have like, t star x. What does that mean? Right? Create a pointer to t, right? So again, if you read it backwards, x is a pointer to a t, right? Where t could be some type like int. So if t was int, x is a pointer to a integer. What does star variable mean? Dereference. And what does dereference mean? It says go to the address where variable is at and get the value that's there, right? Go to the address that variable is pointing to and get the value that is there, right? again, if variables type is, so if over here we have something like t star variable, what's the type of this expression, star variable? It's just t, right? So you can think about the ampersand, right? If we have some hints over here, right? This adds 1 star to var's type, right? In terms of like typing, so whatever var's type is, ampersand var is 1 more star than that, right? Or again, when you put a star in front of a variable, right, you remove a star from variables type, right? So the number of stars you put in front of the variable is the number of stars that you remove from its type. And one of the things that you can try to do to make sure that you're doing things correctly is that the types line up. The type on the left-hand side should be equal to the type on the right-hand side. And if they are lining up, you probably did it right, though there are definitely still ways to screw that up. Yeah. Okay. Any questions so far? Okay. So let's say we made some declarations over here, right? So here we have like int x, y, z. Or maybe we should probably do something like, a equals 5, b equals 10, z equals 43, right? This is going to create 3 variables, a, b, and c, right? Who have the values 5, 10, and 43, and again, addresses completely made up. So maybe 100, 217, and, 313, right? Those are their addresses. So if we did ampersand a, what do we get? 100, right? It's the address of a. And again, when you're working with pointers, putting these tables down will be really, really helpful for you to understand what it is that you're doing and what memory looks like. So we can also, yes, this is ampersand a. It is indeed 100. But we can also declare other things. Like maybe we have like an integer pointer, p1 is equal to the address of a. When we do this, right, we create a brand new variable, p1, right? Its value is going to be equal to 100, and it might be at address 125, right? If I do this, int star star p2 is equal to the address of p1, what's this do? Right, here's p2. What value does it have? 125, and maybe our address over here is 223. Cool so far? Right? We might now also have like another pointer integer p3 is equal to the address of b. And so over here we have p3. What value does it have? 217, and it's going to be at address maybe 569. Right? Notice that the types on the left-hand side, they match the types on the right-hand side. Right? We said that we put ampersand in front of a variable, we add 1 star to that thing's type. So here a's type is int, so ampersand a's type is int star, and what do we have on the left for p1's type? Int star, right? They line up. Over here we have p1, what's p1's type? Well, it's int star, so ampersand p1, its type is int star star, right? And p2's type, they line up, right? Same thing here, the address of b, right? It's going to be int star, and p3 is also an integer star, right? How many stars can you put in front of a variable? Well, I mean, like when you declare a type, right? You can, yes, do any number of stars. But after that variable's been declared, how many times can you dereference a variable, I should say? How many times can I dereference A? How many times could I dereference A? Yeah. It's the number of stars the type has. So how many times could I dereference A? 0 times, because A, right, how many stars does it type have? 0, so you cannot dereference it, right? P1, how many times could we dereference it? Once, because it has 1 star. P2, 2 times, right? P3, 1 time, right? And again, if we want to go like even crazier, we can do something like int star star star, you know, P4 is equal to the address of, say, P2. And then over here we have P4. It has what value in it? 223, and maybe it's at 619. Right? Is this making sense so far? So when I dereference, say, P1, what am I going to get? Right? This says get the value that P1 points to. So we go to P1. Where does P1 point to? What address? 100, right? The value that P1 stores is an address, so we're going to go to address 100, and then we're going to get the value that's there, which is 5. Right? If I do star P2, what am I going to get? So we look at P2, right? And this says go to where P2 points to. What address do we point to? 125. So go to address 125, get the value that's there. So that's address 100. If we do star star P2, it's 5, right? But again, if we do the work, the first part right here says go to where P2 points to. So we go to where P2 points to, address 125, and then we get the value that's there. So the first part of this expression, star P2, it's 100, right? So then when we have star 100, it says go to address 100 and get the value that's there, which is 5. Any questions here? Okay, so now we could do something like this. What happens if we did star P2 is equal to, let's say, P1 plus 117? What's going to happen here? Right? So what's in P1? $100, right? That's 100. 100 plus 117 is 217, right? So if we break down this expression, we now have star P2 is equal to 217. So what does this expression here say to do? Go to where P2 points to, go to address 125, and change the value that's there to 217. So this gets updated, right, to become 217. And so now if I do star P1, what do I get? Right? This says go to where P1's pointing to. Where's P1 pointing to? 217. Get the value that's there. It's 10, right? So in doing this line, what do we make happen? We made P1 point to B, right? Any questions here? Okay, so if you guys are all cool with that, let's talk about what you can do with pointers besides what pointers are. So the first thing that you can use pointers for is to modify the value of a parameter that gets passed to a function, right? And so our rule of thumb here is if you want to be able to change a variable of type x, type x in a function, you must pass at least a pointer to x's type, or pointer to x. So if we want to be able to change an integer, our function needs to accept a integer pointer. If we want to be able to change a character, character pointer. If we want to be able to change a double pointer. If we want to be able to change an integer pointer, integer pointer pointer, right? One more star than its type. Come on. So let's say over here I wanted to write a function that swaps two variables. Let's say we want to be able to swap two integers, right? So over here we might have something like void run swap. And then down here I might have int a who's equal to 10 and b equal to 5. 10, b equal to 5. And essentially we want to be able to say, what? Sure, doesn't really matter, it has some values. So we want to be able to swap a and b, right? And then, after we do this, we'd hope that, a should be equal to 6 and b should be equal to 10, right? So over here, what should the signature of my swap function look like? First, does it return anything? No, so its return type should be void. Its name is swap, and we want to be able to swap two things, x and y. What are the things whose values we want to change? Integers, right? So if we want to be able to change integers, what should our function accept? Integer pointers, right? So these should be integer pointers, right? Because down here, the things we want to change in this function are ints, so our function needs integer pointers, right? And as long as you're thinking through this step, you'll be fine with the pointers, right? Do I want to change that argument, right, in the function? If your answer is yes, make sure your function accepts a pointer to it, and you'll be absolutely perfectly fine. If you don't want to change it, accept whatever its type is. Because C does what's called call by value, so you end up with a copy of the element. So what code should we put here?
Dereference x to a variable.
So int temp is equal to star x, so we save a copy of the value of the variable.
Star x is equal to 10. Star y is equal to 10.
Star x probably needs to be equal to star y. Then star y is equal to temp. If we do this star y equals temp ahead of time, right, then we'll have lost the original value. And again, I'll show you like a visualization of this in 1 second. And now over here, right, our function, it wants pointers to the variables that it wants to swap. So what should we pass in here? The address of A and the address of B. So let's see this in action. And again, if you're working with pointers, Python Tutor, fantastic website, but just go to the C version. So over here we have our swap function. And what I'm going to do is I'm going to write it incorrectly the first time, and then we'll write it correctly the second time. Right? So over here, a lot of times people might make this mistake. Int x, int y, x, x, y, y, no ampersand, no ampersand. So let's visualize our execution. And we give it a moment because it takes time. Okay, here we go. So over here, notice we're in main. We have A and B. Their values get initialized on this line. So we have A is equal to 10 and B is equal to 6. So now when we call this function, C uses something called call by value. So you create, whenever you pass a variable to a function, you actually pass a copy of its value. So we create two brand new variables, x and y, as well as our new variable temp. So now notice what's changing in the code. So here, right, temp ends up equaling to 10. X is going to end up equaling to 6, right? And then y equals temp, right? Y equals temp. So y is going to become 10. So now notice, what have we changed here? X and y. What did we want to change? A and B, right? Now our function ends and our local variables get deleted, and we go back into main, and what we had didn't get edited at all, right? Didn't get changed. So if we swap this back to what we had before, the correct answer, star, 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 ampersand, ampersand, and we visualize our execution. Oh, yeah, that's not going to work. And hopefully this goes faster than last time. Oh yeah, integer pointers, my bad. Yeah, I don't know why it's busy, or if it's just because I'm trying to stream this at the same time I'm using this, and that's why it's slow. So over here, right, again, we create A and B, their values get created, but now we're not going to be passing copies of A and B, we're going to be passing the address of A and B. So over here we have X and Y, and they now point to A and B. So when I do this line, temp equals star X, right, whose type is incorrect, because it should be an integer, right? The type on the left should match the type on the right because we removed one star from X. Its type is int, so temp's type should be int as well. So stepping through again. So over here, they're pointers. So this line says temp should get whatever X points to. X is currently pointing to A, right? X is pointing to A. So temp should get whatever X points to, so it's going to get the 10. Now over here, we're saying go to where X points to and change its value to wherever Y points to. So we go to where X points to, which is the A, and change it to the value that Y points to, the 6. So A ends up changing to be 6. Then we say, go to wherever y points to and change its value to be whatever temp is equal to. So we go to where y points to, that's B, and change its value to be equal to 10. We now finish, x and y get deleted, and we end up returning 0. I mean, we end up completing the function, but the values have been swapped. Does this make sense? Any questions here about this first use of pointers? Does anybody need an additional example? Okay, just have one person come to office hours. We'll do more examples. So let's talk about a couple of other things. So there are 4 sections of memory, right? And let's make this big like the other one was big. Everybody gets 14 fonts, so everybody in the back can read it. So there are 4 types of memory. There is the text section, there is the data section, there is the stack, and there is the heap, right? So each of these has different stuff that's stored there. So what's stored there? And it also has a lifetime. How long does it last? So the text section of memory, what it stores are your program's instructions, right? The actual things that say to add, subtract, multiply, divide, etc., move values around. How long do you think this section of memory lasts?
Indefinitely.
Well, not forever, but as long as the program is running, right? So as long as the program's running, right, the text section of your program is going to exist and the instructions will stay in memory. As soon as your program finishes memory, that text section will get cleared to make way for other things that need to use memory. There's the data section. This is where global and static variables are stored at. And these also, last for the lifetime of the program, right? So they last just as long as the data section exists, right? So as long as the program's running, the static variables and your global variables are going to exist. The stack, this is where your local variables and arguments. And how long do they last for? Any guesses? Right? They last, until the function ends. A slightly more technical definition is until they go out of scope. But if you just say until the function ends, I'm happy with that. Then there's the heap. This is for dynamically created memory, right? So sometimes this stack section, it's referred to as automatic memory because space gets created when you need it, right? When do these variables get created? When you call the function, right? And function call, and they get deleted when you don't need it. The function ends. Then there's dynamically allocated memory. It lasts until you say to delete it. Right? And this is what our next topic will be about in a moment. How do we create space here? Right? It lasts until you say delete it. So this is sometimes referred to as programmer managed memory. Because You create it. You delete it. It's up to you. It's your responsibility, right? Before we go into this, I want to show you one thing. Oops. So here is our little function. So over here we might have like integer pointer p is equal to fun. And then, we might say, int a is equal to star p. What do you expect p's value to be after doing line 26? And let me go put this over into the Python tutor so that we can see it happening. So what do you expect to happen here? Yeah. So we expect that a will be set to 10, and let's see what happens. Oh, gosh. Okay, so over here, right, we're going to create p and a. They're already going to be created. So over here we call our function. So we create a brand new function x, right? Then we say return x's address. Maybe x's address is 100. So this function ends up returning 100, right? But then how long does x last for? Until the function ends. Oh, it got deleted, and you now have a pointer to something that's been destroyed. And so when you attempt to do this assignment, what happens is undefined. I don't know what's going to happen. Different compilers will do different things, and you'll end up with different values. So one key takeaway point is never return pointers to things that are on the stack, right? Because if you return a pointer to something that's on the stack, right, a local variable or an argument, it will not exist after the function ends, and so you'll end up with a pointer to something that no longer exists, and terrible, horrible, no good, very bad things happen, and debugging these is a nightmare, and it's very painful. So don't do this. Sound good? So finally, let's talk about Heap, how to make memory there. I guess I want a .c file. So the functions that you need to be able to do dynamic memory allocation, they are inside of stdlib.h. So if you want to use these functions, you're going to have to include it. And there's three main functions here. There's Malloc, there's calloc, there's realloc, and I guess there's a fourth one, which is free. So Malloc and calloc, they both dynamically allocate space. You also have free, which releases dynamically allocated space. Releases, deletes. So one key thing that you need to have here is that every, Malloc / calloc needs to be paired with a free somewhere along the way. So what I'm saying here is if you make 10 calls to Malloc, you're going to need 10 calls to free. If you make 17 calls to Malloc, you're going to need 17 calls to free. They're not going to be right next to each other because you're probably not going to create the space and then immediately delete it. You'll create the space, use the space, finish using the space, delete the space.
What is the difference between Malloc and calloc?
We'll show you in 1 second.
And my other question, where does free come from? Like, where is this space? Is this like a...
So this space, yes, it's in your RAM.
Okay.
And it's on the heap section of your program. And then Realloc, it resizes dynamically allocated space. So if you make space for, say, 10 things with Malloc, and later on find out that you need 20, you can use Realloc to resize that space to make it bigger. Or if you find out that you allocated space for 100 elements, but you realize that now I only need 20, you can use Realloc to shrink that 100 space down to 20 elements. Make sense? So over here, we might have a function called integer pointer make array using Malloc. And then here we might ask for an int num elements. And so what this function is going to do is it's going to make an array of integers num elements big. So the way that this works is you would do something like integer pointer AR is equal to Malloc. And then inside Malloc, you specify how many bytes worth of space that you want. So how many bytes do you want? And I'm really going to emphasize bytes, right? Here, what's our goal? What do we want to make? Again, what was the goal of this function?
Make an array of integers?
Make an array of how many integers?
Num elements.
Right? So if I say num elements here, this makes num elements what? Does it make num elements integers? No, it makes num elements bytes. So to make the appropriate amount of space, you have to multiply by how big each thing is. And if you want to know how big something is, you use size of. And size of will tell you the size of a variable's type in bytes. So here you could say times size of. We want to multiply the size of a int. So you can say size of int. And this will now allocate that many elements. Right? But it's really important to remember to multiply by the size. Because if you don't multiply by the size, you probably won't have enough space. Right? An alternative way of specifying the statement so that you never get the wrong type here is instead of saying size of int, another thing that you can do instead is you can say size of, oh gosh, come on, star whatever's on the left-hand side of the equal sign. Because what size of is going to give you? It's going to give you the size of the type of this expression, right? So size of expression gives you the size in bytes of expression's type. So what is the type of this expression? An integer, right? And the way that you can figure out that is AR's type is integer pointer, right? And so if you put a star in front of AR, gosh, you remove one star from its type. One star from its type. So if you remove a star from its type, you end up with int, and so you'll always be right. You'll never get this wrong, as long as it's one more star than what's on the left-hand side. Right? And then here we would just say return AR. Does this make sense? Now, this space that Malloc creates, the space created by Malloc is uninitialized. So the space that's created here, its values are undefined. I don't know what they are. There's garbage there, but you have the space to put things. Sound good? Now, what Malloc is going to give you back is Malloc returns a pointer to the first element in the array. This ends up working because the elements will all be right next to each other. So if back here I asked Malloc for, say, 5 elements, right? I did something like integer pointer AR is equal to Malloc 5 times the size of an int here. What it's going to do is it's going to create space for 5 elements. 0, 1, 2, 3, 4, and 5, right? The values that are in them, I don't know, 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 and I don't know. They're random garbage. This space, though, will be created in memory. So maybe this first element, it's at location 200. So where is the second element going to be at? 201 and 2 and 203 and 204 and 205. When you dynamically allocate space with a single call to Malloc, the elements will be next to each other, right? So here's a little secret. When you do something like this, AR at I, this is equivalent to doing star AR plus I, right? And so what Malloc is going to return back over here is the 200. So over here we have AR, and its value is going to be equal to 200, right? It has the address of the first element in the space that you allocated. So now when I do something like this, AR at, say, 3, this again translates to be star AR plus 3. So I'm just going to put some random numbers in here so that we can actually say something. So maybe this is 9, -8, 65, 23, 74, 99, right? There's random garbage there. But I'm just putting some values so that we can work with it. So when we do star AR plus 3, how does this translate? Right? So what's the value of AR? AR's value is 200, right? So this is star 200 plus 3. Well, what's 200 plus 3? 203. So this expression says to do what? Yeah, dereference address 203. Dereference 203 means what? Go to location 203 in memory and get the value that's there, which is 23, right? This is if we this is like the address, the index, and then the value, right? So this ends up being equal to, in our example, 23. Does that make sense? Any questions here? Yeah.
Like the values, like number of elements should be 5 instead of 6?
1, 2, 3, 4, 5. Sure. I made a mistake there. Any other questions? Okay. So now let's say over here I want to make an array using calloc. And again, int num elements. The difference between malloc and calloc is calloc takes 2 arguments. The first argument is the number of things that you want. The second argument is how big is each thing. I would always recommend using calloc over malloc because you'll never forget to put in the size of the thing if using calloc because it requires 2 arguments. So integer pointer AR is equal to calloc, the number of elements, size of star AR. Return AR. Makes sense. Right? It just requires 2 arguments instead of 1, so you won't ever forget to multiply. But I show you malloc because it exists and people use it. So I would say always use calloc. Calloc will also initialize all of the bytes that you allocate to be 0. So the array will be filled with zeros with calloc, whereas malloc is uninitialized. Any questions about calloc? So over here, we might do something like integer pointer AR1 equals make array with malloc, and we might ask for 7 things. So this is going to make us an array of 7 big, and we could do something, like for I equals 0, I less than 7 plus I, AR1 at I, is equal to I plus 23, right? You can fill it in, put the values there. Right? If we want to make our array using calloc, it's going to be the same thing. Integer pointer AR2 is equal to make array calloc. And then again, you could ask for something like 8. And then you could do whatever it is that you felt like with them, right? So, fill them in. With maybe like I times 2. Right? So the values can get filled in. We can print them out later on if we want. But let's say that we finally finish, right, with the space and we're done with it. We have to make sure to release it. So you say free AR1, free AR2. It doesn't matter how much space that you allocate, right? Free will be able to take care of it, right? It's just the number of calls to malloc and calloc have to be equal to the number of calls to free at the end of your program, right? So in these 2 function calls, each one of them made one call to malloc, one call to calloc. So we need to free it when we're done. If we forget to free it, we have what's called a memory leak, and this memory cannot be reclaimed, right? An example of probably where you've experienced this before is how many of you guys have ever played a video game, and the longer you've had it open, the slower and slower and slower and slower and slower it's gotten until you finally had to close it. That's someone probably left a memory leak in the code, and so what kept happening is the program kept asking for more and more and more and more and more memory, but it never let go of the memory when it was done with it. And your computer has a finite amount of resources on it, so there was less and less and less for it to run with, and so it performed worse and worse and worse until you finally had to go kill the program and start it over again. Any questions about free? Yeah.
What would happen to the array 1, 2, after you free it?
So after you free it, the memory gets deallocated, right? And you shouldn't be trying to use it. So at this point, trying to dereference AR1 or AR2 is undefined behavior, and I don't know what's going to happen. But the space has been released, and you no longer have ownership over it, so you shouldn't try to use it. There's another question? Yeah.
Does free only work on memory pointer to a memory created in the heap, or does it also do it, if for some reason I wanted to do it for a variable on the stack?
So you can only free things that you've dynamically allocated using malloc, calloc, and realloc, right? You cannot just free some variable on the stack. Attempting to do so is undefined behavior, and I don't know what's going to happen, but you'll probably crash your program. Yeah?
So could you please explain why it is better to use calloc instead of malloc?
It's better to use malloc instead of calloc because it's better to use calloc instead of malloc because it's really easy to forget to do that. Now, did I make enough space? No. Does it look like I made enough space? Yes, right? But I forgot to multiply by the size of. Whereas with calloc, right, since it requires 2 parameters, if I forget to do one, the compiler's going to be like, that's not how you call calloc, and complain at me and it won't compile. And you'll be like, oh, whoopsie, I forgot to put that in there, and then you put it back and you'll be good. I think there's one other question, maybe? Yeah.
For Malloc, is that supposed to be I less than, oh, sorry, calloc down, is that supposed to be I less than 7? Or is this I less than 8?
It should be I less than 7, because remember, you use 0-based indexing. If there's 8 things, there's 7, if there's 7 things, it's 0, 1, 2, 3, 4, 5, 6.
No, it says no elements.
Oh, for here, sure. If I wanted to fill them all in, absolutely, I would need 8 here. You had a question?
Yeah, so we free it after we're done with using the array?
Yeah, you free it when you're done using it. And your question might be, when am I done using it? My answer is, it depends on your program, right? When you no longer need it, it should be fairly obvious to you. Delete it then. Does that make sense? Okay, finally, there's realloc. Realloc is used to resize an array. So over here, right, we might have, void resize array. And so here's something interesting. We're going to need to take an integer double pointer, and you'll see why in 1 second. So here's our integer double pointer AR, even though we're resizing only a single dimensional array. The way that realloc works is you say, what is it that you want to realloc? Well, I want to realloc star AR. And then you say what its new size should be in bytes. New size in bytes. Again. So don't forget to multiply by the size of. So over here, AR, new size. So over here, we say what our new size in bytes should be. So we'll say something like new size times the size of. And then again, you can always put star of whatever's here on the left-hand side. So star star AR. So this will resize our array. If new size is bigger, space is added at the end. So if, for example, we had like 1, 2, 3, 4, 1, 2, 3, right? And we resize to be, say, 6, right? We're going to still have the 1, the 2, and the 3 there, but then we're going to have, I don't know, I don't know, I don't know, right? The space gets added at the end. If new size is smaller, then space is removed from the right. So again, if I originally had 1, 2, 3, and I resize, or maybe 1, 2, 3, 4, 5, and I resize down to 2, I'm going to just be left with 1, 2. Sound good? Now, there's a couple of interesting things that you can do with Realloc. If you resize to 0, it is the same as calling free. So if you resize down to 0 elements, you'll free it, right? And if you resize null, it behaves like Malloc. Null isn't something that we've discussed so far, but null is sort of equivalent to Python's none. And what null means is this pointer does not point to anything. So null means this pointer currently doesn't point to something. Right? But null can only be used for pointers. right? You cannot say something like int x equals null or double y equals null. It's for pointers only. This pointer currently does not point to something. Dereferencing null will always crash your program with something called a segfault. A segfault simply means you are trying to access memory that you don't have permission to access. Yeah.
So if you resize it to null makes the array value to.
No, not if you. So if the new size isn't null, if you do something like this, let's say we have like integer pointer AR2 is equal to Realloc null 10 times the size of star AR2. This is the same thing as doing integer pointer AR2 is equal to Malloc 10 times the size of AR2. So if you attempt to realloc the null pointer, it behaves like malloc and it will just create space.
What does Realloc reference?
So when you realloc space in memory, it's possible that realloc might need to move where your array is at. So what might happen is we currently have our value like 1, 2, 3 over here, right? So 1, 2, 3, right? And again, let's say we want to resize to 6. Resizing to 6 big. It may be that 1, 2, 3, right now, the memory right next to it is like in use, right? So we might have it where again like 1, 2, 3. If we pop back over to pointer examples, right? Again, here's our array. Maybe it's at like address 300, 301, 302, right? And then here were our values. Maybe just they're A, B, and C, right? And we want to realloc. But over here at 304 and 305, it's already in use by something else, right? Since we want to resize to become bigger, right? But this area in memory is already in use, realloc might have to go move your array somewhere else where there's enough space to fit it. So right now, we might have like, AR is equal to 300 because that's where our array begins at. But after we do the realloc, we might need to move those values. So maybe we now go over to address 400, 401, 402, 403, 404, 405, right? And now we end up with A, B, C, question mark, question mark, question mark. But we have 6 elements now. And now AR is going to be equal to 400 because realloc had to go move where our array is at. It'll only do this if it has to, but you never know when it's going to have to. So it's always really important that whatever you realloc over here, you make sure to reassign to whatever realloc returns. Because if you didn't do the assignment and realloc moved it, okay, great, here's your array at address 400. And if you had forgotten to do the assignment, AR would still be 300, and this memory would now have been freed because realloc had to move it and it would go and release the old space of memory. But now when you went to go dereference your array, you're going to get some segmentation fault, probably, because that memory is no longer in use. So, right, this is, each of these guys would become freed when we did the movement. But if you hadn't updated AR is still going to point to here, and then dereferencing AR to access the elements will cause problems. Any other questions? So now you might ask, well, why did I have to accept one more pointer than what I wanted here? The answer here is if we go to resize our array, think about this. Let's say we want to resize our array, and we want to resize array 2 to fit 20 elements. In our function, do we want to change AR2? Think about this. We took this parameter over here, AR. Did we say it's equal to something? Yes, we said it was equal to something. No, we did not. There's an equal sign right here. So yes, we would try to assign it, right? Right? I want to change AR in that function. I'm trying to say AR is equal to something, right? Because if I was doing this outside the function, I would just say AR2 is equal to Realloc, right? 20, right? Realloc AR2, size of, star AR2, right? Here is AR2 being assigned to something. Yes? No? It's definitely being assigned to something, right? You can see the equal sign right there. It's not a trick question. So, do we want to be able to change AR2 in our function? Yes? No. We do want to change it, right? If we want to be able to change a variable inside of a function, right, what do we have to pass to that function? A pointer to it, right? What's AR2's type? Integer pointer, right? So if I want to be able to change an integer pointer, my function must accept a integer pointer. And that's why I ended up with 2 stars up here. Because I'm trying to change it. Does that make sense?
So you say Realloc will it change the value of AR?
It can, right? If we go back to our example, if this space was not in use, right? If it was, free and free, right? What would have happened is we would have ended up with A, B, C, right? Our original value. And then we would have had, our new values that popped up over here.
So isn't that, can you go back?
So here, right, it's not always guaranteed to be changed, but it can be changed, right? So if it doesn't move it, it will just end up returning back 300 again.
But isn't it has to be star AR?
Yeah, because look, I'm assigning, right? If I want to be able to change AR, I need to receive at least a pointer to whatever AR's type is. I want to be able to change AR2, so in order to change AR2, my function has to accept a pointer to its type. So we would need a star, which we get with an ampersand, right, to add an additional star there. Does this make sense? Any questions? Okay, let's do something fun then.
Yay!
Right? Actual practical applications. So probably one of your favorite functions from Python with lists is append, right? Add an element to the end. That doesn't exist in C, so let's go write our own append function. Now in terms of problem solving, right, you really want to think about what it is that you want to do, right? So here we have append, and what should our parameters be? An array, right? Do you want to append to an array of integers, an array of characters, an array of doubles? Sure, I mean, like, does it really matter? No, right? So we have our array over here. So like integer pointer AR. And what else do we need to know about it? if we're doing an append?
Size, length.
We need to know its size, right? And probably the value that we want to put there, right? So we want to append some value to our array. What should our return type be?
Poly.
Right? I mean, we can leave it up for debate later on, right? But, so right now we have a unknown return type. So when we think about what we need to do here to make the append happen, what happens with an append? Not in terms of code. What happens? You add something to the end, right? So if I originally started with something like 1, 2, 3, and I want to append 4, right, we're going to end up with 1, 2, and then 4. In order to add that 4 there, what do I have to do first? We have to resize the array so that it can fit this new element. Then I can go put it in. So first, right, resize the array to fit the element. And then we add it at the end. So how do I do the resizing? We use Realloc, right? Again, we're assuming that this space has been dynamically allocated. If you try to realloc a statically allocated array, again, undefined behavior, because it wasn't created using Malloc or Realloc or calloc. So over here, right, we have AR is equal to Realloc. What do I want to resize? AR. How big do I want it to be? Length plus 1. But again, this is going to give us length plus 1 what right now? Bytes, but we want length plus 1. Length plus 1. Integers, right? So we need to multiply by the size of, again, star AR, or again, if you want to write int, they'll do the same things, but you're never going to get wrong if you do star whatever's on the left-hand side. So, right, we've made the space, and now we need to go put the element in. So how do I put the element in there? AR at, so right, at this point in time, oops, this should be 1, 2, 3, 4. At this point in time, what's length? 3, right? But if we look at indices, this is index 0, 1, 2, and we want to add it at index 3. So what should our index be, given that our original length was? Array at length is equal to value. Do we need to do anything else? So our array got bigger, right? But when we return back from this call, what's length going to be? Right? When we started, right, in our example, array's length was 3. So the value of, the array's length was 3. We resized it to be 4. But what's len right now? 3. So shouldn't we probably make that bigger? Right? To let the user know that it's bigger instead of them having to manually increment it every single time. Right? So I could do like len plus equals 1. Now, are there any problems with my code? Yeah?
I don't know, but shouldn't the length be an integer pointer or?
Notice we wanted to change the value of our parameter, and we want that change to show up where we called it, right? I want to change length, which is an integer, so my function is going to have to accept a integer pointer, one more star than what it is. So yes, this had a star missing, and now this needs a star here, and then we need a star here, and then we need a star here. Same thing with what? AR, right? Notice we're also changing AR. Hey, look, AR equals. Do we want that change to show up outside? Yeah, so our function has to accept a pointer to the array. if array's type is integer star, our function needs to accept star star over here, which means we need to go add some extra stars. So add a star here, add a star here, add a star here, add a star here. And again, we don't need to return anything, so it's void, but I will let you know about a subtle error. The square brackets, they have higher precedence than the dereference operator, right? So in this operation right now, first we're going to do something like this. Oops, here. We're going to, oh gosh, come on. Surround it with parentheses, thank you. We're first going to go len past array and get the element that's there, and then dereference a second time. Now, does that make sense to what we want to do? Again, a drawing of this would probably help, but I don't really much time. So again, in our example over here, when we call append, right? So we might say, you know, I want to append nope. Extract into variable. Place all occurrences. AR1 length. So over here we might say like I want to append 43 to the address of AR1, and it's the address of AR1 len long. Right? This will go add the value there to the end. Now, in this statement, right, we might have here's AR1, right? It currently has some values. These values might be at address, you know, 300, or I don't know, 500, 501, 502, and so on, right? There's elements that are in there. So AR1, what value does it have in it? 500, right? AR1, though, is also a variable. Let's say in our example that the address of AR1, because it's a variable, it lives somewhere in memory, is equal to 600. Sound good? So if we look at this expression here, right, we're saying take whatever AR is, but notice this is a pointer to it, so I'm going to rename this guy ARP. So ARP, its value is equal to 600, right? So now we do 600 plus our length, right? So you do 600 plus your length. Let's just say our length is 3. 600 plus 3, right, is going to be equal to 603, right? 603. Do we have, and then we're going to go to address 603 and then dereference it a second time. Now, do you see 603 showing up anywhere in our example? No, right? So that's the problem of what's going on, right? First, what we would like to do is do something like this. If we do star ARP is equal to what? Right? So remember, address of A1 is 600, AR1 is at 600. So if you dereference ARP, you're going to go to address 600 and get the value that's there, which is 500, right? So if we did star ARP, right, at 3, star ARP is 500. 500 plus 3 gives you 503, which is where our element's supposed to be at. So to fix this, and do it correctly, parentheses. Otherwise, you'll get a lot of very fun and hard to debug errors. So watch out for that, because there's a lot of subtleties as to things you can screw up. We'll do one more thing quickly. Let's say we wanted to make a matrix. So integer, let's do double pointer make matrix, And then here we have int num rows, int num calls. Right? So the way that this ends up working is here's my double, oh my goodness, we can do this, double pointer mat. It's going to be equal to calloc num rows times the size of, or no, size of here, size of, oh my goodness, star mat. This will make space for our row pointers. Then, for I equals 0, I less than the number of rows, mat at I is equal to calloc. This should be num rows. Num calls times the size of star mat at I. And then we could return mat. So this will make a two-dimensional array. And if you're going to delete it, so void delete mat, that's int num, or so we're going to delete a double star mat, int num rows, int num calls. What we need to do is kind of do the deleting in reverse. So for I equals 0, I less than num rows, free mat at I, free mat. And that will delete it. One thing I should note is that when you delete the space, this does not change mat at all. Notice mat, its value hasn't been assigned to anything. So it's still pointing to that old deleted space. Free will not set you to be equal to null. So just watch out for that. So mat's value is some portion to some unallocated portion of memory. We'll probably actually get into what we're really supposed to talk about on Thursday. If you do have questions, though, about pointers or anything we're going through, stop by office hours. Remember, you guys have priority right now for like the next hour and 15 minutes.
When?
Let me just stop this.